Welcome back to my class. In the world of electric or electronic circuits, many a times we need to simplify those circuits to represent them in simpler form, or maybe to know the response of that circuit. And there are many methods which we can apply to simplify them. One of the important methods is Kirchhoff's voltage law or mesh analysis, which we frequently use. Now, I will cover this law in two classes, and I will discuss about this law, how to apply this law, and we will be solving numericals based on that law. So today's class is the first class on KVL. It says that the algebraic sum of all the voltages or voltage drops in any closed path or loop of a network that is traversed in a single direction is 0. So first we will understand that what it means. Here we have an electrical network where we have two passive elements, two resistors having values R1 and R2, and a voltage source having value V. Now as we can see that this is a closed path. Now in this closed electrical circuit, if we start traversing from any point of this circuit or network, then what will happen as per this law is we will consider all the voltage values of all the voltage sources and all the voltage drops that will take place across all these passive elements, and then we will take the algebraic sum. So as we know that the voltage also has the polarity, and that is also very important. So we have to consider the polarity of every voltage value. For this electrical network, the polarity of this voltage source is already shown, that is given, and say this voltage source will supply a current I in this circuit. Now since R1 and R2, these two are connected in series, so this I current will flow through both of them. So when I current will flow through R1, then if the voltage drop across this resistor R1, if it is V1, and the voltage drop across R2 if it is VR2, then as per Ohm's law, VR1 will be the current that is flowing through the resistor, which is I, and the resistance value, which is R1. Similarly, across R2, the voltage drop VR2 will be or can be written as I into R2. Okay. Now we know that the current flows from higher potential to lower potential, and the current direction through R1 will be from left to right, and similarly through R2 it will be left to right. That means as per that convention, the polarity of VR1, this will be at higher potential this side, and this side will be at lower potential. Similarly for VR2 also, this will be at higher potential this side, and this will be at lower potential. Now the polarity of all these voltage values are now determined. Next is to develop this algebraic sum and as per the law. Now if we start our journey from this point of this network, and if we go by the direction of the current, then first element that we come across is the voltage source, next is R1, and then R2. So there is a convention where when we will apply this law, we have to follow a convention. The convention is if suppose when we are traversing from negative terminal to positive terminal, we can take that voltage in that algebraic equation as per the law, we can take that voltage as positive voltage. So whatever convention we are following from negative terminal to positive terminal when we are traversing, if we take that voltage as positive voltage, then we have to follow that convention throughout our circuit. So suppose for the time being we are following that convention. So from this point when we will start our journey, then we first voltage value that we are coming across is V, and from negative to positive terminal we are traversing. So this will be taken as positive voltage. So plus V, then the next value is VR1, which is I into R1. So here also we are traversing from positive terminal to negative terminal. So this voltage will be taken as negative voltage. Negative to positive, if we consider that is a positive voltage, then when we are moving or when we are traversing from positive terminal to negative terminal, then that voltage will be taken as negative voltage. So this voltage value, which is I multiplied by R1, that will be taken as negative voltage. So it will be I R1. Then again the next voltage value is VR2, which is I multiplied by R2, and since we are again traversing from positive terminal to negative terminal, so this time also the voltage value will be taken as negative. So it will be minus I R2, and as per the law, the algebraic sum of all the voltage values, voltages or voltage drop, that will be equal to 0, and that will happen in a closed path or loop of a network, and we should traverse in a single direction. So here we have a closed path and we are traversing in a single direction. We are starting from this point and we are traversing as per the direction of the current, and we can traverse in the opposite direction also. So that doesn't matter. And these are the three components that we have in this circuit, and we have considered all the voltage values, and the algebraic sum of these voltage values will be equal to 0. So what relationship we are getting? V is equal to I into R2. Now this is one convention when we move from negative terminal to positive terminal of a voltage value, then we consider that as a positive voltage. And I said that even if we follow the opposite convention, then also we will get the same result. So now if we suppose follow that when we are moving from negative terminal to positive terminal of a voltage source or voltage drop, then if we consider that as our negative voltage, then what will happen for the same circuit, that we will see next. So from negative to positive terminal we will consider as negative voltage. So again, if we in the same circuit, if we start traversing from this point along the direction of the current, then the first component is the voltage source. So this voltage source, and the value is V, and we are traversing from negative terminal to positive terminal. And this time we have assumed that from negative to positive terminal, when we are traversing, that voltage value we will be considering as negative voltage. So this time the V will be taken as minus V, and the other two voltage drops, for them, as we have seen earlier, that we are traversing or we are moving from positive terminal to negative terminal. So this time for both the voltage drops, we will be taken as positive to negative. This time it will be positive voltage, so it will be plus VR1 and then plus VR2, and that will be equal to 0 R2. Now we can see that initially also when we assume this convention, from negative to positive we assumed as positive voltage, we followed that convention, we finally got this relationship V is equal to I multiplied by R1 plus R2. And this time in the second case, when we followed the opposite convention, from negative to positive terminal, we assumed that that voltage as negative voltage. So that time also we finally got the same relationship, V is equal to I multiplied by R1 plus R2. That means in case when we follow Kirchhoff's voltage law, when we do mesh analysis, definitely the polarity is important for a voltage source, but what convention we are following from negative to positive terminal when we are moving, whether that voltage is taken as negative voltage or positive voltage, that doesn't matter. Finally we will get the same result. We will finally reach to the same equation or expression, but we have to keep in mind that whatever convention we are following for that particular circuit, that how many components that circuit has, for every component, for all of them, we have to follow the same convention. If we follow the same convention for all the components in that closed circuit, then we will get the same result finally. Next is we will see that in a series circuit, how the voltage is divided among all those components which are connected in series. Now in this circuit, as we can see, we have three resistors. Say for them the values are R1, R2 and R3. They are connected in series with each other, and with them there is a voltage source having value V, and that is also connected in series. So this is a closed circuit or closed path, loop, whatever you say. And in this closed electrical network we have four components, one voltage source and three resistors. Now we will see that this we will see that how the voltage is divided among all these passive elements in that circuit. Now for that also we will take help of mesh analysis or loop analysis or KVL. So if we apply KVL in this closed circuit, so say this voltage source is supplying current I, and since all of them are connected in series, and we know that in case of series circuit the current is the common factor, so through all of them the current that flows is same. So I current will flow through all the resistors. Now if the voltage drop is VR1 across R1, and if it is VR2 across R2, and if this voltage drop is VR3 across this R3 resistor, and this, since current is flowing from left to right for all of them, so this will be positive terminal and this will be negative terminal, higher potential to lower potential. This will be at higher potential, this will be at lower potential. Similarly for VR3, this is higher potential, this is lower potential. Now if we apply KVL in this closed circuit, suppose if we start traversing from this point and if we follow the direction of the current, then first element, the first voltage value that we come across is the voltage value. And suppose we are following the convention that when we are traversing from negative to positive, then we will consider that voltage as negative voltage. So from negative to positive, this V we will write as minus V, and then for this VR1 and for every other voltage drops across this passive element or resistor, they are the polarity is same from positive terminal to negative terminal. So for all of them it will be written, all of them will be taken as positive voltage. So in the equation, in the algebraic sum will be written like this: minus V plus VR1 plus VR2 plus VR3, and that will be, as per the law, it will be equal to 0 plus R3. Now if we want to find out the main current which is supplied by this voltage source, we can easily find out. I will be equal to, now if we want to find out the individual voltage drop across R1, R2 and R3, then they can be written as VR1, we know it is I multiplied by R1. So I we have already found out in terms of the voltage value, the supply voltage value. So it is V upon R1 plus R2 plus R3. Similarly for VR2 we can write, it will be I multiplied by R2. I is the same value, V upon R1 plus R2 plus R3 into multiplied by R2. Now we will solve a few problems using mesh analysis or KVL. Now in the first problem, the problem statement is find out the current value that which is flowing through 5 ohm resistor in the following circuit, and this is the circuit diagram. So here in this circuit diagram, as we can see, we have 1, 2, 3, 4, 5 resistances, the passive elements, and we have 2 current sources and 1 voltage source. Now what we need to find out is the current value through this 5 ohm resistor. We have to, since we are in this class we are learning mesh analysis or KVL, so we will apply KVL or mesh analysis. But how to decide whether we will apply KVL or KCL? We know that in case of KVL, in that equation all the values are in terms of voltage value, voltage drops, or maybe the value of the voltage source. So in a circuit, if we see that all the values are voltage drops, or all the sources, they are the voltage sources, so easily we can the first thing that will come in our mind is that we will apply
KVL or mesh analysis. Second thing is, if we see that most of the components in that circuit are connected in series, and also we can identify the different loops in that circuit, then also we will try to apply KVL or mesh analysis, and that is the thing that will come in our mind first. But in a circuit where we have mixed sources, like if we have few voltage sources and few current sources, in that case it becomes a bit confusing that which law we will apply, Kirchhoff's voltage law, and next we will learn there is another law which is Kirchhoff's current law. So here in this circuit, this is an example of that kind of circuit where we have voltage source as well as current source. So which law now we will apply? So far we have learned KVL, about KVL only. So we will not think of KCL, but once we are familiar with KCL, Kirchhoff's current law also, and if we get this type of circuit to simplify, then the confusion will arise that which law to apply first and which law will give us the solution faster. So in this circuit, though we can see that there are current sources along with voltage source, one thing also we can see that for both the current sources, for this current source, there is a resistance which is connected in parallel, and in this parallel in this part of the circuit, here also we have a current source, and with that current source we have a resistance connected in parallel with that current source. And there is a concept of source transformation that has been already discussed in earlier video. You can refer the link given in the description box, that any current source, if it is connected, a current source if it is connected with resistance in parallel, then that current source can be converted or transformed into a voltage source, and that resistance will be that time after transformation, that resistance will be connected in series with that voltage source. So that logic or that transformation rule can be applied for both the parallel branches, because here the current source is in both the cases the current source is connected with the resistance in parallel. So now if we transform this part of the circuit, here this current source will be converted to a voltage source, and if we convert or transform this current source to a voltage source, then we in the modified circuit we will see that we will have resistances definitely, and the energy sources, every energy source will be voltage source only. So easily we can apply KVL or mesh analysis. So first thing what we will do here is we will transform the current, both the current sources. Now again we know that for that transformation we follow Ohm's law. So here the current value is given and also the resistance value is given. So the voltage value of that transformed voltage source will be, for the first case, the voltage value will be the current value, which is 10 multiplied by resistance value, so it will be 20 volt. And in the second case, for this part of the circuit, the voltage value will be, and with both these voltage sources, their corresponding resistance will be connected in series. So in the next step, what we will do, we will redraw this circuit, and in that circuit we will have all these 5 resistances, but we will have all the energy sources as voltage source. So this is the circuit. So this current source and this resistance, they are connected between these 2 points in the original circuit. So what will happen after transformation between these 2 points, we will have now a voltage source, and in series with that voltage source we will have this resistance, the same resistance. So this is in the modified circuit. Say this is the point, a pair of points between which these 2 branches were connected in parallel. So we will connect the series part, the voltage source and resistance, between those 2 points only. So this is the voltage source having value 20 volt, and this is the resistance value. Now what will be the polarity of the voltage source? That has already been discussed in that video. Since the current is flowing in upward direction, so the polarity of the voltage source, it will be here the positive terminal, and at the bottom it will have the negative terminal, because when this will supply current, it will be in this direction. because we know that from voltage source, from the positive terminal, the current comes out, or it flows in that direction. So this will be the current direction of the current if when it will supply current. So it matches with the direction of the main current source. Now then after this we have this resistance 10 ohm, then we have this parallel branching. So this has already been transformed into voltage source. So instead, and these two current source and this resistance, they are connected between these 2 points. So finally, after transformation, when we will connect the voltage source and this resistance in series with that voltage source, they will come between these 2 points only, and this is the connection in the modified circuit. So we will have this voltage source instead of this current source. Voltage value we have already found out, which is 5 volt, and this resistance, same value will be connected here, same resistance will be connected here, and they will form a series connection, and they will be connected between these 2 points, same points. Now after that we have this 5 ohm resistance, so here it is, and then we had this resistance value, and with that in parallel this voltage source. So it has been kept as it was in the original circuit, and this time the voltage source is connected in parallel with this resistance value. So it's not current source, it's voltage source. So this is and already since we want to apply KVL or mesh analysis, so we want voltage source to be in the circuit. So finally in the modified circuit will look like this. Now in this circuit, if we analyze closely, we can see there are 3 individual loops in this circuit. One loop, this is first loop, this is second loop, and this is third loop. So here we will be doing loop analysis or mesh analysis. So first thing is, in the first step, we have to identify how many different or individual loops are there in that circuit. So in this circuit, as we can see, there are 3 individual loops. And then after identifying the individual loops, what we have to do is we have to assume loop currents in every loop. So in the first loop, and all the currents will be flowing in the same direction as per our assumption. So if we are assuming that all the currents in all these individual loops are flowing in clockwise, if current in one loop is flowing in clockwise direction, say for this loop, I have assumed that in this loop the current is this loop current is flowing in the clockwise direction, and the current value is say I1. Similarly, when for the second loop I will assume current, the direction of the current will be same as this. I have assumed that it is flowing in the clockwise direction, so in the second loop also the current direction will be same as, but it is not mandatory that the direction of the loop current has to be in the clockwise direction. It can be assumed in the anti-clockwise direction also, but whatever we assume, that has to be again maintained same in the whole circuit. So if we assume the direction of the current in all the loops in anti-clockwise direction, finally we will get the same result or same values for I1, I2 and I3, or whatever we want to find out. But whatever we are assuming, the same convention or same direction we have to follow for the whole circuit. Now the identification of the individual loops are done, and we have already assumed the current values for these loops and their directions. Now in every individual loop, what we have to do, we will apply the concept of KVL or Kirchhoff's voltage law, and we will develop voltage equations. So in the first loop, if we apply KVL, so what we have to do, this is a closed path, so we will start our journey from any point in that closed path. Suppose if we want to start traversing in the first loop from this point, and if we follow the direction of current of the first loop, and that is clockwise, so first voltage value that we will come across is 20 volt. Now again, when we are moving from negative terminal to positive terminal, if we assume that value is negative, that voltage value is as negative voltage, then it will be in the first equation, that value will be taken as minus 20. Then after that, the next component is this resistance 2 ohm, and the voltage drop will be current, which is I1, which is flowing through this, and multiplied by the resistance value. So it will be I1 into 2 for this 2 ohm resistance. For 10 ohm it will be I1 into 10, and since current is flowing from left to right for both of them, so this will be at higher potential as we have seen in earlier case. This and this will be at lower potential. For the second one also, this will be at higher potential, this will be at lower potential. So in the equation it will be multiplied by 10. Then if we follow the direction of the current, then the next component that we are coming across is this resistance, 1 ohm resistance, and the net current which will be flowing through this resistance, it will be not only I1, because in the first loop the current that is flowing through this 1 ohm resistance is I1 current, but in the second loop the current value that we have assumed, which is I2, so this current is also flowing through this 1 ohm resistance. So through this 1 ohm resistance is not that only I1 current is flowing, I2 current is also flowing. I1 is flowing through this 1 ohm resistance downward, and I2 current is flowing through 1 ohm resistance is in upward direction. So net current, since we are now analyzing the first loop, we are in the first loop, so with respect to that, the net current which will be flowing through this 1 ohm resistance resistor, that will be I1 minus I2. So it will be we have to remember, when we have a common component between two loops or meshes, then the current that will be flowing through that particular component, it will not be only one current which is associated with one loop, it will be the resultant current which are flowing through which are flowing in both the loops. So for 1 ohm the I1 current is flowing in downward direction, and again through that resistance the I2 current is flowing in upward direction. And since we are analyzing the first loop now, so with respect to that, the net current which will be flowing through this 1 ohm resistance, that will be I1 minus I2. Now this will be, since the resultant current now it will be I1 minus I2, with respect to that, this the voltage drop that we will get across this 1 ohm resistance, that it will be at higher potential and this will be at lower potential. So the voltage drop which will be written for this 1 ohm resistance, that will be the current value, which is my I1 minus I2 multiplied by the resistance value. Then next element is the voltage source. Polarity is given, so we are traversing from positive terminal to negative terminal, so this time it will be plus 5, and then algebraic sum of all these voltage values as per KVL, it will be equal to 0. So finally what value we will be getting, what equation we will be getting is 10 plus 2 plus 1, so it will be 13I. Then for I2 it will be, there is only single I2, so 13I1 minus I2, and then minus 20 plus 5, so it is minus 15. So if we take that constant on the other side, that will become plus 15. So this will be our first equation that we have developed from our first loop. Then next what we will do, we will come to the second loop. In the second loop, again if we start traversing from any point of that loop, and if we apply KVL, then we will develop another voltage equation from that loop. So suppose if we start traversing from this point in the second loop, and if we follow the direction of the current, so first component, direction of the current, it is flowing in the clockwise direction, so we will also move in clockwise direction. So first component that we will come across is this resistance 5 ohm, and the voltage drop in that case for that resistance will be, the current flowing is I2, so it will be I2 multiplied by 5, and then we have this component. Again this is a resistance which is common between these two loops, and we can see easily that through this resistance, 10 ohm resistance, the I2 current is flowing in downward direction and I3 current is flowing in upward direction. So net current through this 10 ohm resistance, it will not be only I2 or I3, it will be the net value of I2 and I3. So that will be, since now we are in the second loop, we are analyzing with respect to that. So the net current through 10 ohm resistance this time will be I2 minus I3. So the voltage value for this 10 ohm resistance will be this. Now we are in the second loop with respect to that direction of current. This will be at higher potential, this will be at lower potential, and the voltage value will be I2 minus I3 into the resistance value, which is 10. After that, the next component is 5 volt voltage source, and this time we are moving in upward direction through 5 ohm this voltage source. So we are basically traversing from negative terminal to positive terminal. So this time the voltage value will be taken as negative voltage and minus 5. Then the next component is this resistance 1 ohm, and this time the current value, we are in the second loop, so resultant current through this 1 ohm resistance will be, it's not I1 minus I2, this time through 1 ohm resistance it will be I2 minus I1. So I2 is flowing in this direction, I1 again in downward direction, and we are in the second loop. With respect to that, the current now in the second loop that we will consider resultant current through 1 ohm resistance, it will be I2 minus I1. And the voltage drop this time will be, so with respect to the direction of I2, this will be at higher potential, this will be at lower potential. So it will be plus I2 minus I1 multiplied by the resistance value, and we have already covered all the components in the second loop, there is nothing left. So that will be equal to, algebraic sum is equal to 0 as per KVL, so that will be written as 0. So if we simplify this equation, we will get, here we have I1, I2 and also I3. Finally, we can see we have only one I1, so it will be minus I1. We have one I2 here, 5 I2. Now if we rearrange the terms and we simplify further, then the final equation that we will get in terms of I1, I2, I3, that will be minus I1. Then in the same manner we will also apply KVL or loop analysis. We'll do loop analysis for the third loop. So in the third loop it is simpler than the other two loops. In the third loop we have only two components. Now if we start traversing from any point, say we want to traverse from this point, and we will follow the direction of the current, which is I3 this time. We are in this loop now. So the first component that we will come across is first the 10 volt voltage source. So it will be first that for the 10 volt voltage source, this is the polarity, from positive terminal to negative terminal we are moving. So it will be written as plus 10, and then we are traversing through this resistance 10 ohm, and this time we are in the third loop, and through this 10 ohm we already know that both two currents are flowing, I3 and I2. So this time the resultant current will be I3 minus I2, and polarity of the voltage drop, that will be also different this time. So I3 minus I2 will be, I3 is flowing upward and I2 is flowing downward, and with respect to the direction of I3, the voltage drop that we will get across this 10 ohm resistor, this will be at higher potential and this will be at lower potential. So the voltage drop that we will be getting across this 10 ohm, that value will be I3 minus I2 is the current value multiplied by the resistance value, which is 10. And since we are moving with respect to this current, we are moving from positive terminal to negative terminal of that voltage drop, so this will be taken as plus a positive voltage, the voltage drop that we will be getting across this 10 ohm resistance. And we have only two components in this loop, so algebraic sum of both these values will be equal to 0. Now if we rearrange the components, then the final equation that we will get, it will be 10, all have 10, so 10 is common, so it will be I2 minus I3. So we have already developed three equations in terms of I1, I2 and I3. All these three are variables, and now we have to solve these three equations to get all the current values. But the requirement was the current value that which is flowing through 5 ohm resistor. We have to find only that current value, means this resistance values or this resistor. So we know that in the circuit, in the modified circuit, if we look, that through 5 ohm resistor only I2 current is flowing. So if from these three equations, after solving these three equations, if we can only find out I2, that will be sufficient for this problem. Otherwise, if we want to find out, or if we want to know the voltage drop across any other resistance value or current flowing through any other resistance, then we have to solve for other variables. So here for this problem, if we solve only for I2, that will be sufficient. Now in these three equations, as we can, by looking at these three equations, we can understand that this is the simplest form. So here this equation is associated with I2 and I3, but finally we want to find out I2. So what we can do is here, from the third equation, we can replace, or we can represent I3 in terms of I2. So if we do that, then from the third equation, the relationship that we will get is I3 will be equal to I2 minus 1. And then in the second equation, which was minus I1 plus 16 I2 minus 10 I3 is equal to 5. Then in that equation, if we put I3, the value of I3, if we replace I3, then the equation will be finally in terms of I1 and I2. So let's rewrite that third equation, second equation, minus I1 plus 16 I2 and then plus minus 10 I3, which was equal to 5. Now in this equation, it has all the current variables I1, I2 and I3. Now in this equation, what we will do is we will replace I3. So 10, and in place of I3 we can write I2 minus 1, and that will be equal to 5. We can name this as our fourth equation. We can mark that as, and first equation that we developed, that was 13I1 minus I2 is equal to 15. So let me rewrite that equation again. 13I1 minus I2, and that is equal to 15. So now what we can do, we can solve these two equations to find out the value of I2. Minus 0.649 ampere. That means the current value as per the direction that we assumed in those loops was clockwise. So as per that direction, the current through 5 ohm resistance is flowing as per our assumption from left to right, and that value is minus 0.649. That means actually the current is flowing, it's not from left to right, the current is flowing from right to left, and that value is plus 0.649. So either way we can think that if the current, we think that it is flowing from left to right, then that value will be minus 0.649 ampere. That means that the current is actually flowing from right to left. 0.649 ampere current is flowing through this 5 ohm resistance from right to left. So this is the way how we can apply KVL, the concept of KVL or mesh analysis, and we can simplify a given electrical network in step-by-step approach. So in the next class we will solve a few more problems by applying KVL or mesh analysis method.